So just like Noetherian rings, we can talk about Artinian rings. A ring R is Artinian if a descending chain of ideals eventually becomes constant. So in Noetherian you had ascending chain of ideals, in Artinian you have descending chain of ideals. So say you have ideal I1 which contains I2 which contains I3 which contains In and so on. So eventually this will become constant for some n greater or equal to n naught. So I of n naught will be equal to I of n naught plus 1, which will be equal to I of n naught plus 2 and so on. So exactly like it was in Noetherian, but the inclusion sign is reversed. So instead of ascending we have descending. Equivalently, every non-empty set of ideals contains a minimal element. So this is exactly dual to what we have in Noetherian. So in Noetherian you had every non-empty set of ideals contains a maximal element. Here in Artinian we have every non-empty set of ideals contains a minimal element, and the proof is essentially the same with this inclusion reversed. So now from Artinian rings we can go to Artinian modules. So a module M over a ring R is Artinian if decreasing chain of submodules of say Ni contained in M eventually becomes constant. So say you have the submodules Ni of M and you have a descending chain like N1 contains N2 which contains N3 which contains Nn and so on. So eventually after n greater or equal to n naught, these modules become constant. Exactly here these two are the same. Here we are talking about chain of submodules, here we are talking about ideals. So equivalently, every non-empty set of submodules contains a minimal element. Now we talk about important distinction between Noetherian and Artinian rings and modules other than being descending and ascending. So a module is Noetherian if and only if each of its submodules are finitely generated. There is no such equivalent condition for Artinian modules. So for Noetherian you have this finitely generated condition, but for Artinian you do not have it. So Noetherian are much more useful than Artinian because you can prove a lot more things because of this finitely generated condition. Now second important point is that this Cx is a Noetherian ring. So this we saw through the Hilbert basis theorem, because C is a field, so it is trivially Noetherian because it just has 0 and C itself as the only ideals. So you adjoin X to it, so this will also be Noetherian by Hilbert basis theorem. But it is not a Noetherian C module. So Cx is a Noetherian ring but not a Noetherian C module. Now since it has an infinite dimensional vector space over complex numbers, and the base is given as 1, x, x square, x cube and so on. So this will become important because we will see that the Cx is Noetherian but not Artinian. Now let us do some examples. So first some non-examples. So this integers is Noetherian but not Artinian. So you have this 5z is contained within 25z. So this is 5 square. This is contained within 5 cube z all the way to 5nz and so on. Now this ring kx1 x2, this is neither Noetherian nor Artinian. So you have this sequence of ideals which is increasing, and it continues increasing because there are infinitely many variables which we have attached here. So this keeps on increasing. So this is not Noetherian. It is not Artinian also because this x1 contains x1 square which contains x1 cube and so on. So there is no minimal element here, so this chain will keep on going on. Now instead of x1, if we just write x, then you can see that this Cx, which is a Noetherian ring, it is not Artinian because it has this chain of modules like this or chain of ideals like this which has no minimal element. So you can see this is a chain of ideals in say Cx, and it has no minimal element, so it is not Artinian and it is Noetherian. Now we want to construct something dual to this, so that it is Artinian but not Noetherian. So consider this G as a subgroup of rationals modulo integers. So that is, it has only rational numbers, and all the integers you can say are just zeros in here. So G is a subgroup consisting of all elements, say whose order is a power of 5. So G has fractions like this: a divided by 5 to the n, where a is an integer and n is a natural number. So then the only proper subgroups of G are G to the power of n of order 5 to the n for each n in natural numbers. So G is Artinian because you pick up every non-empty set, say of submodules, will contain a minimal element. So because it will contain elements like this is an increasing chain, but it is not Noetherian. So you always have this minimal element which is just integers, because integers, then you modulo out integers, this will become 0. So G1 would contain of elements like this: a by 5. So we are going to modulo z out because it is rationals modulo z, so this becomes 0. So you always have the minimal element, but you do not have any maximal element. So say 7 by 25, this lies in G2 because the denominator is of the power 2 and its order is also 25. So order of Gn is 5 to the n. So order of this is 5 square, because when you multiply it by 25 you get 7, which is an integer. You modulo out integer and you land back up in G0. So you get the order. So obviously this element has order 5, but if you multiply it by 25, this will just become an integer. You modulo integer out, you will again land up here in G0. So again you have to modulo integers out. So if you take any non-empty set of submodules, it will always have some minimal element because you can arrange them by this, but there is no guarantee of having a maximal element. So this is this G is Artinian but not Noetherian. So notice that how this example and this example, they are dual to each other. So you have 25z here, you have dividing by 25 here, so and so on. So we finally come to examples which are both Noetherian and Artinian. So for any field K, it is trivially both Noetherian and Artinian because only non-zero ideals are 0 and the entire field itself. And if you have V is a vector space which is finite dimensional vector space over some field K, then we can form strictly descending or strictly ascending chains of vector spaces by arranging them by dimension. So thus for a finite dimensional vector space, it is Noetherian if and only if it is Artinian. So because you take any chain, so you take any chain, say C1 contained within C2 contained within C3, this will stabilize at the top by dimension. So you have arranged this, so it will stabilize at the top by maximal dimension, it is stabilized at the bottom by the minimal dimension. So the chain is always finite. So this chain is always finite, and therefore it is both Noetherian and Artinian.